Hi students, I hope you're all doing good. So welcome to this module on image restoration and reconstruction. So to say briefly or to summarize about what you have learned previously, so in the module 1 we started with the digital image fundamentals. You saw what is digital image processing, the applications, how the human eye visual perception is, and components of image processing system, the way image is sampled and the quantization is done, and most importantly you saw some of the basic relation between the pixels. You saw how the neighborhood, four neighborhood, eight neighborhood, adjacency, all that you saw in the module 1. Okay, so basically you saw the fundamentals of digital image processing in module 1, and then we went to another very beautiful and important module, which was on image, enhancement, where we studied some spatial domain and frequency domain filtering. Okay, so how based on, also you understood, the histogram and how to analyze the histogram, etc. And also you saw how you can, go for spatial domain filtering, right? Some of the transformation functions, some concepts, and also you saw how we can analyze the frequency domain filtering, right? So there, in this module, basically, we went for image, enhancement, right? So we applied few techniques, maybe in spatial domain. We basically first we understood the histogram, then we did some filtering in spatial or frequency domain, okay, based on the kind of data in hand or the image data in hand. Now, this module, of course, we have studied the later modules, that is 4 and 5, we have completed, where you saw the college image processing, segmentation, etc. But in between, this module, of course, was skipped. But now, I think since you have a lot of idea about image processing in hand right now, so image reconstruction and restoration is restoration and reconstruction. The idea becomes very simple. Now you may ask me, ma'am, when I hear this term called as image restoration, it sounds almost close to image enhancement. What is the difference? Okay, so the term looks so close by. So if you ask what is image enhancement, okay, there the principal goal is basically what you're trying to do there. These are some heuristic procedures to manipulate an image and take advantage of the psychophysical aspects of the human visual systems. So we are playing with the human visual system. So image enhancement, so finally is to see through that the human visual perception can get a better feel of the image. That is what you're doing in enhancement. Okay, and it's quite a subjective process. But now when we speak of image restoration, okay, what is it? Let's see the beauty of image restoration and reconstruction in this module. So image restoration is mainly to improve an image in some predefined sense. Now, of course, this is similar to what is image enhancement, okay? But image enhancement is quite a subjective process, but image restoration is an objective process. Now, what is the meaning of that? When we go for image restoration, okay, we should have some a priori knowledge of the degradation phenomenon. So that's why it's the most part of image restoration is an objective process. We need to have some knowledge how that image got degraded. That's based on that we'll apply some particular process to go for image restoration. So we're trying to restore an image. Okay, so we should know how the degradation has taken place in an image. But in image enhancement, it's not like that. So both image enhancement and image restoration both deal with improving an image in some predefined sense. But when we speak of image restoration, we should have the prior knowledge about the degradation phenomenon. So basically these restoration techniques, we need to model the degradation by and apply the inverse process to recover the original image. So as we can see here, the restoration techniques, they are oriented towards we need to model the degradation. Okay, so in the first topic we are going to see some noise models. Okay, so how that degrades, suppose it is been, for example, degraded by Gaussian noise. So we got an image now which is already degraded by Gaussian noise. So what we have to do is we have to model the Gaussian noise and perform a process, and then we have to apply the inverse process to recover the original image. So let us understand that with the help of a simple block diagram. So what you see in front of you is the model of the image degradation or the restoration process. So listen here carefully. Actually, what you get in hand will be this g of x comma y. So g of x comma y is the degraded image. I'll repeat. G of x comma y is the degraded image. So that is what will be as an engineer given to you. Now you have been asked to use some restoration filter to get the enhanced sorry, the restored image. Now what you should understand here is that originally that image would have been f of x comma y, which would have been a good image, okay, a good image. It must, so what we have to do is we have to model this degradation function h. Okay, so this modeling of degradation function or is the actual modeling of the image degradation or the restoration process. Here, this is no, what we are trying to tell is we should have the knowledge of this degradation function h, which should have caused the damage to that original image f of x comma y. Okay, and some a priori knowledge about the noise eta of x comma y. Okay, so our g of x comma y, which is the degraded image, is the result of f of x comma y, which has been degraded. So g of x comma y is the degraded image. So we should have an estimate or we should have the knowledge about this degradation function. So the degradation process is modeled as a the way it is degraded. So I told you in previous slide, we should have the a priori knowledge about how it got degraded. So that is the difference between going for an image restoration process and a image enhancement process. Okay, so I know I'm repeating it, but you should understand here. So we should have the degradation process is modeled as a degradation function h, which actually operates on the input image f of x comma y to produce the degraded image g of x comma y. Okay, so given the g of x comma y, and if you have the knowledge about the degradation function h and maybe some knowledge about some additive noise eta of x comma y, then we can design the restoration filter. Okay, so we can design the restoration filter that can be used to obtain the estimate f cap of x comma y, which should be in very close you know uh, uh, the field with the same as f of x comma y. So the difference between f cap of x comma y and f of x comma y should be minimal. So we have to design the restoration filter that can get an estimate f of x comma y which is as close to the original image f of x comma y. So this is the model of the image degradation process. So I'll repeat here, the image in hand which is given to you will be the g of x comma y, which is the degraded image. As we want to do the image restoration process, we should have the a priori information about how the original image might have been degraded, which is given by the degradation function h. Okay, so degradation process should be known. Also, some information or a priori information about the additive noise eta of x comma y, and thus you will be able to design the restoration filter which can produce an estimate f cap of x comma y, which is very close, or the difference between f of x comma y and f cap of x comma y and f of x comma y, which should be very minimal. So now let us try to understand how we can model the system mathematically. Okay, so as I told you, g of x comma y is the degraded image. Okay, so we need to model or have an understanding of the degradation function h. So the g of x comma y, as you can see in this figure, can be modeled as h of x comma y, which is the degradation function or the spatial representation or the spatial domain or the time domain representation of the degradation function h, which is given by h of x comma y convolved with f of x comma y. So h of x comma y convolution with f of x comma y plus the noise eta of x comma y gives the degraded image g of x comma y. As convolution is nothing but multiplication in frequency domain, it can be represented as g of u comma v is equal to, as you know, the product of h and f as the additive noise n of u comma v, where the h, f and n are nothing but the Fourier representation of h, f and eta respectively. So basically the degraded image can be represented as a convolution of the original image and the degradation function and added with the additive noise, that is eta of x comma y. So these two equations will form the basis for image restoration process in the future. So the main focus of today's lecture will be on the various noise models. So unless we know the various noise models, we cannot design the restoration filter, or we cannot understand how the degradation function h has been arrived at. So one thing I think you must have understood when you saw that figure, your restoration function should be the inverse of the degradation function, so that f cap of x comma y will be a proper estimate of f of x comma y. Did you realize that? It should be, right? So in order to go for the restoration, we should understand how the degradation process took place. So here we need to understand the various noise models. So before we go into the various noise models in this lecture, let us try to understand some or recall some few concepts. We know that when we capture an image, okay, the way we capture an image is very important, because if you have captured the image well, we don't have to do so much of image restoration, image enhancement, etc., right? Okay. So the principal source of noise in the digital image is during the process when we have acquired the image, or sometimes during the transmission over a channel, right? Okay. Now, the when we say we are capturing the image, we have used various image sensors, right? So these image sensors, the performance of them is affected by various factors. What are the some of them? Of course, you can recall there are some environmental conditions, right? The lighting, the quality of the sensing elements, right? So because we are using some imaging sensors, okay? So the CCD cameras, the light levels, the sensor temperature, all these are the factors, okay, which will affect the performance of imaging sensors. Okay, so these are the factors which will affect the way the image has been acquired. Also, there are many problems, or some of in many a times when you're going for image transmission, okay, there can be maybe lightning has occurred or some atmospheric disturbance that can disturb or enter the channel, and this can cause the image to be corrupted or degraded. Okay, so these are the some of the factors you should keep in mind when we are going to understand the various noise models. So before we go into the various types of noise, let us try to understand the spatial and frequency properties of noise. Before moving further, let me make a point here. See here in this subject, in this digital image processing, the image restoration models, what you're going to study, the types of noise models, etc., they are quite superficial level. Okay, so we are going to do the kind of modeling which is in a very nascent or the basic stage, but it is quite good enough to do most of the image restoration modeling. Okay. So here, just to for the sake of better modeling or ease of modeling, we make some of the assumptions. One is that the noise is independent of spatial coordinates. So that is one of the assumptions we make when we go for image restoration modeling. And the other assumption is that this noise which we are going to consider is uncorrelated with respect to the image itself, except for one of the noise which is known as periodic noise. Of course, these two assumptions, when we speak of that noise is independent of spatial coordinates and that the noise is uncorrelated with the image, these assumptions are not always valid and are partially invalid when we go to some of the applications, especially when we speak of applications such as x-ray imaging, nuclear medicine imaging. In all these cases, such kind of assumptions, especially speaking that the noise is uncorrelated with the image, becomes invalid. But the modeling can be quite well enough to arrive at the estimate f cap of x comma y, which is a good estimate of f of x comma y. Now let us see some of the important noise probability density functions. You have encountered these distributions or the probability density functions quite often in either your maths, your communication systems, in ITC, etc. So this is going to be a kind of a review class wherein you're going to recall all these different noise probability density functions. The first one is the Gaussian noise. So you are very familiar with this, that the probability density function of a Gaussian random variable given by z is given as p of z is equal to 1 by root 2 pi sigma into e to the power minus of z minus z bar square by 2 sigma square. Now here we should understand that the z represents the intensity and the z bar is nothing but the mean or the average value of z. What is sigma? Sigma is nothing but the standard deviation and sigma square is nothing but the variance. You can see a plot also is shown here. Okay, so you can see that most of the values will be in the range between z bar minus sigma and z bar plus sigma. Okay, so you can see that the mean is at the center given by z bar. Okay, then also you can see that the maximum value of the magnitude of the PDF is given by 1 by square root of 2 pi sigma. Correct? This is when the power of E is nothing but 0 or the Z bar is equal to Z. Okay, so whatever. So this is how is the probability density function of the Gaussian random variable Z. Okay, I hope this part is very clear. Now, let us go to the next one. So this is nothing but the Rayleigh noise. Okay, so the probability distribution function of a probability density function of a Rayleigh noise is given by P of Z is equal to 2 by B Z minus A Z 2 by B Z minus A into e power minus of Z minus A whole square by B for Z greater than or equal to A and 0 for Z less than A. Here also the values are quite similar and the mean, okay, so Z bar is usually represents the mean. So mean is given by A plus square root of pi B by 4 and the variance sigma square is given by B into 4 minus pi by 4. The representation of the PDF of the Rayleigh noise is given here, as you can see, of P of Z with variance with how the Z is varying. So that is, as usual, the x-axis is Z and the y-axis is P of Z. And you can see this PDF distribution of the Rayleigh function, right? Okay. So you can see how the the mean. You can what is the representation of the mean or the Z bar is given by a plus square root of pi b by 4, okay, or it's shifted here, so square root of b by 2, and here the maximum magnitude is 0.607 into root 2 by b. And you can see that there is a displacement from the origin, and this is the fact that the basic shape of the density is usually skewed to the right. So that's why this is actually the okay. And the Rayleigh density can be quite useful for approximating skewed histograms. Okay, so when we usually encounter some skewed histogram, so this is the best way of approximation. So the next type of noise which you have to recall is nothing but the gamma noise or the Erlang noise. So the PDF of the Erlang noise is given by P of Z is equal to A to the power B into Z to the power B minus 1 by B minus 1 factorial whole into E to the power minus AZ for Z greater than or equal to 0 and 0 for Z less than 0. The distribution is as represented here with P of Z versus Z. Okay, here the parameter should be considered such that the value of A is greater than 0 and B is a positive integer. Okay, as usual, we need to understand what is the mean and the variance. So what is the mean here? So the mean is given by Z bar is equal to B by A and the sigma square or the variance is given by B by A square. So here is the distribution as you can see in the figure. Okay, so this is the gamma distribution. As you can see here again it is the shifted version. Okay, so it is, that's why it is the b minus 1 by a. Next, speaking of the very easy or the common one is the exponential note. Not common but very easy to represent, that is the exponential noise. Again here the probability density function is given by P of Z is equal to. So each time when we are defining the probability density function, we define for greater than or equal to 0 and less than 0. Okay, usually 0 for less than 0, especially for not a non-Gaussian noise. For Gaussian noise, we will see through that the mean is at the the values are distributed around the mean. Okay, where it is z bar. Okay, so the Gaussian is like a bell shape which is uniformly distributed about the center z bar. But rest all okay, they have their own unique probability density functions. So here, when we are speaking of exponential noise, exponential, as the name suggests, you should have a constant for or represented by a, and exponential by the factor e power minus az for z greater than or equal to 0, and 0 for z less than 0. And here we should understand that the value of a should always be positive, that is greater than 0. Here again the mean and variance is represented as the mean is given by z bar is equal to 1 by a, and the variance as sigma square is equal to 1 by a square. If you observe here properly, okay, students, observe here properly, this PDF is actually a special case of your previous gamma function. If you can recall the previous gamma function or the Erlang PDF, if I replace b with 1, so this becomes the special case of the gamma function, that is nothing but the exponential noise. And you are very familiar with the exponential distribution curve. So here you can see, so the probability density function of the exponential noise given by p of z versus z. Okay, so what is the maximum value here? That is a. Okay, so the maximum value is a, and as you go as the value of z increases, okay, you can just analyze here this function. As the value of z increases, you can see that it is exponentially decreasing function. Because why is it exponentially decreasing function, can you think? Yes, because the power of e is nothing but minus az. Okay, so the maximum value is 1 when, okay, so this power is 0, that is the value of e power 0 is 1, and that is a. And as the value of as the value of z increases, okay, you can see that it is a exponential decreasing function for a positive value of a. If you want to have a negative exponential, then the a should be negative. Next is your uniform distribution or the uniform noise. Again, well known to you. Of course, you all have heard all these noise functions many a times. That's why I'm trying to explain it quite faster. So the uniform noise or the probability density function of the uniform noise is given by P of z is nothing but 1 by b minus a. And you're very familiar with this distribution, okay? And where the z is distributed, this is the value of P of z when z is between a and b. Okay, and what is the maximum value? Of course, it is 1 by b minus a. So it is a uniform distribution. And what is the mean here? Of course, z bar is a plus b by 2. So that is the center. If you take a and b, the center is nothing but the mean. So what is the center? A plus b by 2. Same way, what is the variance? B minus a whole square by 12. I hope this is also well known to you. The next, the impulse noise, okay, which you are quite studied actually in image processing itself, is nothing but the salt and pepper noise. Actually, when we speak of salt and pepper noise, we speak of two types. One is the bipolar and the unipolar. So the density function, what you can see here, is that of a bipolar impulse noise or the bipolar salt and pepper noise. Okay. So here the P of Z is given by some PA for Z is equal to A and some PP for Z is equal to B. So we need to define this actually, the value of PA and PP. What can you understand from the figure here? Can you think and tell? Think for a minute. Yeah, so this is an impulse function, correct? So A is there and B is there. So at A, the value is PA, and at B, the value is PP. Here we should observe properly that it is an impulse function. That is, it has a spike or quick value. It's an impulse at that particular point A and at a point B. So the value of at A, at that impulse value is PA, and the impulse value at B is nothing but the PP. So that's all is your simple PDF of a bipolar impulse noise. If this value of P is actually greater than A, then B will be lighter because the value is closer to the higher intensity value, correct? Conversely, if we speak that level A will appear like a dark dot. Now, I told this is a bipolar impulse noise. So when we can make it unipolar? What is unipolar? Only if there is a single value, right? So if one of them, if either PA or PP is 0, then the impulse noise will be called as a unipolar noise. neither the probability is zero and especially if they're approximately equal, then the impulse noise value will resemble nothing but the salt and pepper granules. Okay, so this you should understand very clearly. If neither the probability is zero, okay, and especially if they're approximated equally, then the impulse noise will resemble the salt and pepper noise. So basically for this reason, the bipolar noise is also called as the salt and pepper noise. So basically what we usually deal with is the bipolar noise, which is usually the normal common term used is the salt and pepper noise. Also data dropout, spike noise, all these are the terms that we are going to use for the same impulse noise or the salt and pepper noise or the data dropout noise or the spike noise. When we speak of this impulse function, okay, so these noise impulses, it like the spike, okay, it can be negative or positive value. So usually when we're going for image processing, scaling is a very common procedure or the a function that is applied. So when we are trying to do scaling, especially when you speak of impulse, the impulse correction is usually very large, okay, so we need to usually go for scaling. So that's why the impulse noise is usually digitized as extreme values. Okay, extreme means so there can be when it is negative value make it zero or positive value make it very large. So usually when we speak of salt and pepper noise, what is the color of salt? Salt is white. So that is what is depicts the highest intensity value, or the if it is a 8 bit, that is 255. What is pepper? Usually it's gray or it is black in color. So usually that value is scaled to 0. So that's why the impulse noise is digitized, usually taking A as black and B as 255 to make it two extremes, especially for a 8-bit image. So that is why the name salt and pepper. The salt, that is when B is 255, that is white, and pepper, that is A for 0 when it is black, especially for a 8-bit image representation. Be it any other number of bits used, the maximum value, that is if the b value is say it's 8, it is 2 to the power b minus 1, that is 255. So depending on the value of b, the highest value is given, or the extreme value is given for white, that is nothing but the b value. Okay, so that is why the two extremes making it a impulse as the best or making the impulse noise representation more clear. You want to make spike representation or the the sudden change representation to be very sharp, and this is a process of digitization used especially for the impulse noise. Now that you seen the different types of noise, starting from the Gaussian, Rayleigh, uniform, exponential, etc., etc., let us see some of the practical cases where these noise can arise. These are just few of the examples, and many other cases where you can these kinds of noise can arise. Let us see the first one, that is the Gaussian noise. Okay, usually the Gaussian noise will come to an image mainly due to poor illumination or when there is a high temperature, especially when we speak of electric circuit noise, sensor noise. So such kinds of noise are usually Gaussian noise. Again, it is when there is pure poor illumination or when there is high temperature. Next, when there is a Rayleigh density. So Rayleigh density usually we use for characterizing noise phenomenon in the range imaging. Okay, so usually when we go for range imaging, we go for Rayleigh density. The exponential and the gamma distribution or densities, they are usually that these are the cases especially when we go for laser imaging. And when we speak of impulse noise, all of you might have got the idea till now that when there's a quick transient, okay, switching, sudden sharp in on off, impulses, such cases you can find the impulse or the salt and pepper noise. And the most least of found in practical situation is nothing but the uniform density. Usually noise uniform distribution is a very least case, or the usually such case of a density does not arise, but however it is a useful basis for many random number generators that are used in simulation. So these are the conditions where uniform density modeling is applied. But most of the cases, the Gaussian noise, or the Rayleigh density, or the exponential, gamma, impulse. So these are the different types of noise distribution functions, that will be the process of degradation that can result in the image. So now that you've understood the various, noise types and the probability density functions, and you have a slight idea as to which type of noise is dealt in which kind of cases. Okay. So now let us see one example. Okay. So what you see here is a test image, okay, or a test pattern to illustrate, how, if the various noises get affected to this image, how will it look like? Okay. Correct now. So what you see here is the first one. This is the one, this test pattern when it is affected by Gaussian noise, it looks like this. And if you see the histogram of the image is like this. You can see that here it looks like a Gaussian, you can see the distribution is so Gaussian in nature. Okay. Same way, the same test pattern when affected by Rayleigh noise, you can see again here the pattern is looking like a Rayleigh pattern itself. And here this test pattern is affected by gamma noise. So you can see that the histogram also resembles a gamma pattern. Same you can see here the test pattern affected by exponential noise, and you can see the exponential pattern in the histogram. Same way with the uniform, uniform noise distribution. You can see like it's almost uniform, and then the salt and pepper noise, how the histogram will look like. So this is the result of the histograms due to the adding of the noise, okay, along with the input test image. Okay, so this is how you can observe that when you see the histogram of these different images, you'll get to know you will get some idea about the type of noise that has affected that image. When we considered the noise till now, we had an assumption that the noises are usually uncorrelated with the images and that they are and also independent of the spatial coordinates. So till now, whatever noise we studied, they were independent of the spatial coordinates and they were uncorrelated with the noise. Okay. The noises was actually uncorrelated with the image. But here I told you that there is one exception in the chapter in this chapter which we are studying is the periodic noise. So periodic noise it usually is a result of the electrical or electromagnetic interferences. So when we speak of electromagnetic interferences, it could be in terms of sinusoidal interferences, so on, which can occur during image acquisition. Okay, so this is the on that one spatial dependent noise which we are considering in this module, and this we should understand that since this kind of noise arises due to electrical or electromagnetic interferences, by understanding the frequency domain, by having the idea of how the various frequencies are present, or by analyzing the spectrum, that is the frequency domain representation, with a good analysis, this periodic noise can be significantly reduced using frequency domain filtering. So let us take an example here. So this is an example of an image that is corrupted by a sinusoidal signal, which is nothing but a periodic signal. Okay. This you can see the sinusoidal signal noise which has affected the image. So what we do is we obtain the spectrum of it, and we can see how the frequency is, or the spectrum, and we can remove this this noise by applying suitable frequency domain filtering. So this is about the periodic noise. So speaking of the estimation of noise parameters. So when we speak of periodic noise, just now I told you that we can estimate the parameters or the frequencies present by just the inspection of the Fourier spectrum of the image. Okay. So you saw that the periodic noise will produce some kind of frequency spikes, okay, and we can observe that using some visual analysis. So it is important to infer the periodicity of the noise components from the image. Okay. But this is not always the case. In simplistic cases, this is possible. Okay. So sometimes you need to have some automated analysis in situation where sometimes not the from visual inspection it is not possible to arrive at the parameters. Usually the parameters of the noise PDF, by seeing that, okay, we can estimate some of the noise parameters. One more thing, you saw that in the test image, right? So when you saw the test image and when we corrupted by noise, by inspection of the PDF, I told you that time itself that we can observe or we can have an idea as to which kind of noise has affected that image. So estimation of noise parameters is very important, especially to define the degradation function that has caused the degradation of the image f of xy, which has resulted in g of xy. Now, once we have an understanding of this, we can design the restoration filter so that we can again get the estimate f cap of x comma y, which is an estimate, or which is as good as f of x comma y, or f cap of x comma y minus f of x comma y is very minimal. Okay. So with this understanding, we come to the end of the noise modules section of this module. So in the next lecture, we'll be studying about how we can go for restoration of the image in the presence of noise only, and we'll see how we can do that using spatial filtering. So see you in the next class.